Hello, I'm Michal and this is problem K. In this problem, we are given the sea floor, which has a very peculiar structure, and we have some queries to answer. But before we get to the problem itself, let's explain about the sea floor. So we are given a unit grid of points that is horizontal, that is at the bottom of the sea floor, and for each of those points, the sea floor has some altitude. And once we know these altitudes, everything else is linearly interpolated within each of those unit squares. But of course, if you have a unit square where you have given 4 different values in its corners, there are 2 ways to do the linear interpolation. You can split it either along one diagonal or along the other, and then interpolate within one of the triangles and within the other triangle. And the peculiar property I was mentioning about the seafloor is that you are guaranteed that within each of the unit squares, this interpolation will give you the exact same result, regardless of whether you do it this way or that way. So let's take a closer look at what that means. So we have a unit square, and in each of its corners, we have a prescribed altitude, the values A, B, C, D here. And now we can find an easy necessary condition. If we are interpolating along this diagonal, then the value in the middle will be the average of A and D. And if we are interpolating along the other diagonal, the value in the middle will be the average of B and C. And if we have to have the same interpolation everywhere, we need to have the same value at this middle point. And this means that those 2 averages have to be exactly the same. And this condition is not just necessary, it is also sufficient. And the easiest way to do it, to see why it is the case, is to go directly to 3D. So here we have the 4 corners of the unit square. Here are the given altitudes, and now the information that both interpolations give us the same value means that in 3D the diagonal between those 2 points and the diagonal between those 2 points intersect, and that means that all of 4 corners of the square are coplanar, they lie in the same plane, and therefore it's easy to show that the rest of the interpolation will also be always constant. So the condition that A plus D equals B plus C is actually sufficient and necessary. So this perfectly captures the property of the seafloor. And now we can rewrite this condition as follows: D minus C equals B minus A, or we can also rewrite it as D minus B equals C minus A. Those 3 forms are equivalent, but the green ones are telling us the following: the difference here must be the same as difference there, and the difference here must be the same as difference there. So if we now go back to the original grid, you can see that from this unit square, this difference and this difference in altitudes must be the same, but then from the next square, this difference and this difference must be the same, and so on. So within each column, all of the values are changing by the same amount, and then the same in the next column, and the same in each of the rows, and so on. So from this, we can easily derive an equivalent phrasing for the condition that looks as follows. We will have row values R0 through Rm minus 1, and column values C0 through Cn minus 1, such that the altitude at any given point is the sum of the row value and the column value for that point. It can be easily shown by what we just derived, that these 2 formulations are equivalent, so the floor has the property from the statement if and only if there are 2 such sequences. And moreover, in our problem, all of the values have to be non-negative, and it can be shown that this is possible if and only if both of the row sequence and the column sequence are non-negative. So if the altitudes are non-negative, we can find such sequences, and vice versa. The other direction is obvious. For the former direction, just find the minimum in the grid and then realize that you can set the minimum of the row sequence to 0 and the minimum of the column sequence to that value, or vice versa, or anything in between, and you will get everything as you need. So we will be looking at our problem in context of these row and column values that are summing up to the correct altitudes. And now let's look at the problem itself. In the problem, we are given the specific altitude at some of the points. Our first task is to validate whether this is actually possible, and represents the correct seafloor, at least one. And then we are given a query, and for the query we need to determine what is the minimum possible altitude at that query point. So let's solve this particular task. And now we will draw a collection of points that will represent the information we have given, and we will think about what it tells us. So suppose we have a bunch of points that are placed like this, and a few more. And now whenever we are given 2 points within the same column, the difference in their altitudes is telling us the exact difference between those 2 corresponding row values. And we can take a look at each and every of these pairs within the columns. If there are multiple points within the same column, we just need to take consecutive ones because it already has all the information we need. And I will just use a different color here, because these 2 points, you can see, they are independent from all of the others. And now each of these edges is telling us one piece of information about the row values, and we can take all of these informations together and derive information about the row values from them, and at the same time we can verify whether there are no obvious contradictions. So we can imagine a graph where each row is a vertex, each of these segments is an edge, and in this graph we'll use any kind of graph traversal to find connected components. Within the connected component, each time we are traversing an edge to a new vertex, we can determine its relative value from the previous one, and each time we find a back edge that goes to a vertex that was already visited, we check whether the value at the other end is what we expected. If we find any contradiction, then the input is contradictory. If not, then we will get an information like this. So for instance, if from the top to the bottom here, the change in altitude is +3, here it is +10, here it is -6, and here it is +0, so those 2 are equal, and these 2 points are at the same y coordinate, then now we can symbolically think about it as follows. So if this value is x, then this value would be x +3. Now this value here would be x -7. The one just above it would be also x -7, and the one here would be x -3. So now the smallest possible values for these particular row values would be 0s here, a 7 here, a 10 here, and a 4 here. And independently from those, in a different component, if this is y and this difference in altitude is +5, then this is y +5. So the smallest possible non-negative values here are a 0 and a 5. And we can now do also the same thing with the horizontal segments and derive information about the column values. Once we have done this, we can now take a look at the entire connected components, which I have drawn each one of them in a different color, and find one final contradiction that can appear. And the contradiction is that if you have a red component like this, it's telling you information about all of the points that lie within any of these rows and at the same time in any of these columns. And we can find the minimum of those altitudes, which can correspond in general to a point that was not given. And if we can derive the exact altitude at that point and it is negative, this is again a contradiction. So if we haven't seen any contradictions, now we are ready to answer queries. If we get a query that is completely unrelated to what we know, the answer is 0. It just works. We can extend the altitudes in such a way that everything will be valid. If we get a query where both of the coordinates are from the same component, then we can exactly derive the altitude of this point. And if you get a query like this, where one coordinate is from one component, the other is from a different component, now what can happen is that you can take the minimum row value from one of the components and set the entire component so that these are the row values and the corresponding column values are increased as necessary. You can take the minimum column value from the other component. So for this one we would take the 0 and something. If this was the query point, we would be taking at least 10 from the row values and something else from the column values, And the sum of those two minima is always constructible and is obviously the necessary minimum. So that's the answer to our query, and that's the last step of our solution.